With that said, I will just kind of get started. So, as far as science goes, where we've been, if you haven't been with us the last week or so, we've been going through the life science section of the GED, which is big. It's the biggest chunk of material that is covered on the test, and so we've spent a lot of time and trying to go through things relatively quickly, but it still takes a while. So this week we will hopefully finish up life science and then kind of move on from here. At the end of last week, last Thursday, we started talking about animals in general and the sorry there, I kicked my desk, but talking about evolution, talking about natural selection, so survival of the fittest, Charles Darwin, that whole thing, and also looking at kind of some adaptations that both predator and prey animals have or share, and just kind of talking about basically traits that animals have that help them be more adept at surviving and thriving. Okay, today we're going to kind of continue that conversation and kind of shift it a little bit, and we'll just kind of see how much we get through. But I'm going to start obviously right here up this slide, so hopefully everyone can see this. This is kind of what's known as a cladogram. And a cladogram shows kind of where traits diverge over time. So we've just kind of got this random assortment of animals, and from left to right, so from hagfish on down the line to chimpanzee, we have more evolved animals or more complex, right? And so I'll just kind of work us through this, and you can follow along, and we'll just go from there. So here we have a set of different traits. These are like physical traits. So jaws, right? Jawbones, lungs, claws or nails, feathers, fur, mammary gland, right? So mammals, right? And so if we go and we kind of go down the line here, you can see we have a hagfish is relatively simplistic, not evolved particularly well. So they lack all these things, right? But they still are able to survive, and we can discuss that more in depth. But really, the bigger takeaway is that a hagfish is basically not very adept at surviving, right? And there's a reason why there's fewer of them. You've probably never heard of them, right? They're relatively simple. But as we go from a hagfish, which has none of these traits, to a perch, which of all of these traits, the only thing they have are jaws, that helps out a lot, right? And so you could lump kind of all fish into this category, right? Fish don't have lungs or claws or feathers or mammary glands, so that limits their potential. But just the fact that they have jawbones and are able to eat food easier makes them pretty good survivors, right? And more so than a hagfish. So you can kind of see the difference and envision, if you didn't have a jaw, how that would impact your survival. You would be much less efficient when it came to eating food and what kind of food you could eat. You'd be more limited, right? And so that's maybe a better way to look at this is how limited are you as a survivor or as an animal in general? Like a hagfish is very limited. A perch, still pretty limited, right? A perch can't just decide they want to, climb out of the lake and live in the desert, right? They have to stay underwater. So, which brings us to our next evolutionary trait, which is lungs. So And you can see where each of these traits provides a little more uh, ability to survive in a wide array of places. These traits also um, tend to be linear in time. In other words, uh, animals develop jaws first, then lungs, and then claws and nails, and it kind of went uh, throughout time. Theoretically, right? These traits evolved afterwards, right? So all of life at one point was underwater until the first animal developed lungs and was able to live outside of the water, right? And again, these are all theories, and I can't definitively, decidedly say this is exactly what happened, but just in kind of talking in big, broad generalizations, right? Animals couldn't survive out of the water until they had evolved to be able to breathe, right? And so the salamanders, amphibians, not amphibians, yeah, where they're able to survive in water and on land. These were some of the first time or the first animals to really be able to live for any period of time out of the water. And none of these traits are things that animals developed, overnight. These are things that slowly evolve over time, and they evolved that way because, you know, animals found out through trial and error it was more beneficial to have jaws than it was to not have jaws. Same thing with lungs, right? So you start to see, you know, salamanders, newts, all of these different amphibians that now are able to breathe and survive outside of the water, but then they need to go back in the water, and they need to stay close to the water, right? Now, if you compare a salamander with a lizard, first of all, a lizard is a reptile, but so that implies that lizards really can survive away from water for long periods of time. Now, like any animal, you need water eventually to survive, but the lizards have adapted, obviously, to live in deserts, very hot places, places where there isn't always a lot of water. The other thing is, if you think about a lizard versus a salamander, if you've ever seen both of those things, one has claws and one doesn't. So what benefit do claws have? Well, they can climb easier, right? So salamanders can't climb up and scale up a tree or a building or a rock very easily. Whereas a lizard, because they have claws to grab onto stuff, can climb up surfaces pretty fast and pretty easily, pretty efficiently. So that's a good thing in terms of for them to be able to survive. Also, defense, right? If you don't have claws, you aren't able to protect yourself or defend yourself against predators nearly as easily as if you do. Okay? So as we move down the line, right, you kind of see where we're going here. As we go from lizard to pigeon or fill in the blank, right, any bird, the big difference is birds have feathers. Birds also have wings, right? So birds now, can fly, which means they can go from place to place much faster and more efficiently than a lizard or something without wings. And the idea of evolving to have feathers means you can stay warm, right? So you don't think of lizards surviving in the winter in places where it's cold and snowing, right? Now, some lizards are more adept at surviving cold than others, but ultimately lizards are cold-blooded and need warm weather at some point in order to survive, right? Whereas a bird, because they have feathers, they're able to survive much, much colder temperatures, right? And again, like everything, some birds more than others, right? Where if you have a pigeon versus a penguin, right? Penguins have much smaller, much more dense feathers, which means they can survive cold temperatures, right? But the point is, as you go down the evolutionary chain, the jump from having just claws and feathers, or claws and nails, sorry, to feathers is a big jump. And that jump is largely related to warmth, right? And then finally, you have animals, mammals, right? So again, it doesn't matter what mammal we're talking about, any mammal here, right? Chimpanzee. They have, again, fur, which is helpful for insulating, right? But they're also mammals, meaning they are warm-blooded. They don't rely solely on the environment to give them warmth or body warmth, right? They can generate their own warmth, just physiologically. And so, and they can also provide food for their young, right? Mammals will have milk to feed their young, which means what? Their young are going to be more likely to survive because they're not fully dependent on their parents bringing in outside food because the mother has food built into their bodies. A pretty big evolutionary jump, which is why mammals are the most successful organism on Earth when it comes to survival, right? There's mammals everywhere. Okay, so that's a cladogram kind of in a nutshell. So I want to talk about energy flow. So food chains and food webs. So organisms move energy and move matter. Producers, so if we look at a food chain, right? A food chain is kind of an oversimplified linear series of feeding relationships. In other words, you have the bottom of the food chain, and then the next step, and the next step, and the next step, okay? It's not necessarily how real life is. It's not that simple, but in terms of getting an idea of kind of how things work, it provides kind of a basic structure of here's the relationship between producers and consumers. That's really all that a food chain is showing. So organisms move energy and move matter, right? So when we talked about energy way back a few weeks ago, we talked about the fact that energy doesn't really disappear, and it doesn't just come out of thin air, right? It can't be created or destroyed. Energy just flows through a cycle. That same concept of energy applies to life, right? When we're talking about life, energy doesn't die off, and energy, it doesn't come out of nowhere, right? And so at the bottom of the food chain, we have producers, and producers are plants, essentially. Plants or algae, anything that uses photosynthesis to harness the sun's energy and create their own energy, right? We call them autotrophs. They're creating energy on their own, right? Well, with the help of the sun, right? So producers don't need to eat anything because they just absorb sunlight and water and produce energy that way, okay? They're the bottom of the food chain. The next step up, well, if we were to look at it just as a two-step food chain, right? You have producers, which are things that make energy, and you have consumers, which are the animals that then eat the producers and gain energy from them, okay? So consumers, again, would be defined as animals or organisms that eat other organisms to survive. So they are called heterotrophs because they need other sources to then provide them food or provide them energy. They can't create energy on their own, right? We've talked about this before, where animals or humans, we can't generate energy on our own. We need to eat something or consume something, and then our body processes that, and then turns that into energy that we can then use, right? That's why if you're really hungry, chances are you feel tired, even if you have slept and you're well rested, right? And then you eat, and then immediately after that, you feel you have more energy, right? That's what's going on. So consumers can kind of be split up into primary consumers and secondary. So if you look down here on the bottom, the food chain, this would be the food chain of an owl. Okay, so again, we're just looking at one series of relationships. Bottom, we have a producer, which is the grass or the plants. The primary consumer is who is the organism or what is the organism that's directly eating the producer or consuming that, right? So herbivores or animals that are eating plants, those are primary consumers. In this case, we have a vole or a mouse or a rat or squirrel or rabbit or whatever the animal is, right? We have the animals that are eating the grasses. Okay, that's the primary consumer. The secondary consumers are the carnivores, or the animals that are eating or consuming the primary consumer. Right? So owls don't bother eating grass, but they get energy through this food chain because they consume the vole or the mouse or what have you, right? So again, both herbivores and carnivores are consumers because they are reliant on other sources of energy. Primary consumers eat plants, secondary consumers are the ones eating the primary. Now, when we talk about energy flow in an ecosystem, a food chain doesn't really show us how an ecosystem's energy really interacts, right? It's just looking at a singular, in this case, just the way an owl gets its energy. Right? But food webs, on the other hand, and I'll come back to this slide, I think, depending on time. I want to skip ahead to this, which is a food web. So this is still looking at the food web of an owl. Okay? But notice that the food web consists of many interconnected food chains. Right? So a food web is a more realistic look at how energy is flowing through an ecosystem. Again, still simplified. You can make a food web as complex as you want it to, right? But just on kind of a basic level, right? A food web shows a more complicated relationship in terms of energy in an ecosystem by showing you all of these different food chains combined onto one, right, or one visual. So same thing here. We start at the bottom with producers, right? They're the ones that are producing the energy. Then we have the primary consumers, but think about it, whereas where we have a food chain just shows a singular animal, right? But we know there are lots of different animals that eat plants and grasses, right? So here we've got a cricket, a mouse, and a rabbit. So they're all eating grass, okay? Now, so that's why these arrows are all going up. Notice here we have, so this, let's call this a rat, and this is obviously a snake. So notice where the arrows start to diverge here. So crickets are just food. Again, we're oversimplifying, but just according to this food web, crickets are eaten by rats, but not by snakes, right? So the arrow just goes this way. Mice are eaten by both, the rat or whatever this is, and right, and snakes both. So there's an arrow going both directions and straight up to the owl, right? So mouse is prey for all three of these things, and so there are arrows going in all three directions. Rabbits are just preyed on by owls, so their arrow goes just to the owl. Okay, so the rabbit really isn't getting eaten by either of these two. Right? But these are, again, the primary consumers. These are what we call the first level carnivores or secondary consumers. So again, like we said, these are animals that are eating or preying on the primary consumers. So again, the snake is eating the mice, the rat or whatever this weird animal is, a gopher or a mole, they're eating mice and they're eating crickets. Okay, so again, they're not consuming the grass, they're consuming these guys. And then we have second level carnivores, which are carnivores that are eating, you guessed it, right? They're eating the secondary consumers. Right? So we sometimes call them tertiary consumers because they're removed three layers from the original producer of energy, right? So, and I don't want to spend too much time on this, but my point is that you could keep going and going and going, right? The phrase top of the food chain means, where you finally get to an animal that's not preyed on by any other animals, right? Like above this owl, there could be animals that are eating or killing and consuming owls, right? So again, you can kind of make these food webs as big as you want, and you can include as many different animals as you want. You could try to do a food web for an entire ecosystem. It would just look wild, and there'd be arrows everywhere with all kinds of different animals, right? So again, we don't need to kind of get that specific. But that's food webs and food chains. Sometimes you also see energy flow in this context as circular, right? And that would be because even the top of the food chain animals eventually will die, and they die, and their body rots and gets absorbed into the earth, and they get basically, their remains are reproduced and produce and result in new plants, right? Because they help, fertilize the soil or what have you. And so that's why sometimes you see these energy flow systems as represented by in a circle, right? Because again, energy isn't just created from nothing, and it doesn't disappear. And so that's kind of the point of energy flow in an ecosystem. All right. So with that said, I don't want to go that far. That's going to be our class for tomorrow. Real quickly, I will go over kind of these population interactions and kind of describe these, and then we will maybe end with a question or two, and maybe not. I'm not sure. So population interactions, again, some of the limiting factors. In other words, if you take a group of animals that are all living together in the same ecosystem, obviously there's going to be more of some than others. Some are going to be more successful, some are not, right? And some of the factors that go into that, and again, some of these are obvious, some of these are less obvious. Reproduction, right? How many offspring that animal is producing. Natural resources, right? So how abundant is the food, how abundant is the water, how abundant is the sunlight, all those factors, right? The amount of natural resources. If you're somewhere where there is a limited amount of resources, there's probably going to be fewer animals. Whereas if you're somewhere where there's lots of resources, there's going to be lots of animals. Like the polar ice caps versus the jungles. Polar ice caps, less nutrients, less natural resources, so there's fewer animals there than there are in a jungle, right? Because there's more resources. Space and nesting sites, again, that's pretty self-explanatory. If there's more space for animals, there's more. I need to exaggerate that or competition, okay? So if there's more competition for food, if there's more competition amongst predators, right, then that's going to limit the amount of animals there are. Wastes, diseases, okay? and carrying capacity. So, and those are kind of straightforward. So those would be some things that limit the amount of animals that can exist in an ecosystem. And then I want to talk lastly just about symbiosis. So these three things here, mutualism, parasitism, and commensalism. Mutualism happens where you have two species interacting where both benefit from that, right? An example, let me think of an example of mutualism in a ecosystem where you have kind of a dumb example, but like in the ocean, when you see pictures of either big sharks or whales, what do you see? If you look closely, usually you'll see fish, little fish, swimming right alongside them, and they almost look like they're stuck, right? Those fish are there because they're eating away at the bacteria or the algae or whatever the I think bacteria would probably be the best word, but they're actually eating away at some of the stuff that's covering the whale or covering the shark, and that actually benefits the shark. So that's why the sharks don't eat, right, or scare them off, because that interaction between those fish and the shark, both parties are benefiting from it. And so that would be mutualism. Parasitism is just what it sounds like when you think of a parasite, right? You have something that's living off of something else. One organism feeding off of the other, right? So leeches, right, literally glom on and sucking blood out of the animal they're attached to. That's not benefiting the host animal, that's just benefiting the leech. So that's parasitism, right? And then commensalism is where you have one benefiting and the other not really being affected, right? So I can't think of an example right off the top of my head, but where you have two animals in an ecosystem that kind of coexist, but they're not really doing anything to one another, right? They're just kind of there, and one animal is benefiting from the relationship and the other animal is kind of unaffected, right? If I think of a good example tomorrow, I'll bring it up. But those would be the three different categories of symbiosis, where you have animals interacting with one another. And again, mutualism is they're both benefiting. Parasitism, one's benefiting, one's being harmed. And commensalism is one's benefiting and the other is unaffected. All right. So with that said, since we're already out of time, I will save all the questions for tomorrow. Tomorrow we are going to pick up right where we left off, talk about this a little bit, and then we're going to look at what ecosystems are in general and what kind of characteristics of ecosystems, and then we'll do some practice. Okay. So that's all I've got for today's science class. Hopefully that was helpful for everybody. I will be back tomorrow with more, and till then, hope you have a good rest of your day, and I will talk to you all later. All right, see you guys.